So I think we are live. 0 people as of now.
We can wait a bit.
Well, it might also happen that the counter... 12 people now. This grew faster. This grew fast. Okay, so I think we can wait 1 more minute and then we'll start. So I'll take this first minute and I'll start by thanking everyone that has joined this event. Today, this will go as follows. So we'll have our speaker presenting during the first 45 minutes, and then we will have a follow-up question and answering session. So I will ask you to put your questions on the chat, and then in the end, we will pick up the questions and ask them to Patrick. Okay, so I think I'll start by presenting our speaker for today for our very first session of this year. We have Patrick Fernandes, which is a PhD student, and he's doing the PhD in a joint program between Instituto Superior Técnico and the Carnegie Mellon University, and he was previously an AI resident at Microsoft. Patrick will be presenting some work being done in his group about explainability and its applications to NLP. So I don't know if Patrick has something to say before he starts presenting.
Oh, yeah, thank you for having me. It's my pleasure. And yeah.
Okay, so I'll ask you to start your presentation, Patrick, and enjoy.
Yeah, thanks. Okay. Yeah, so today I'll present about explainable AI and how can we evaluate explanations. To start off, why is this relevant? Recently, deep learning has emerged as the main paradigm in artificial intelligence. Deep learning models have not only beaten many of the previous machine learning techniques, such as decision trees, support vector machines, but they also have achieved state-of-the-art performance on multiple real-world tasks. However, these great improvements come with a cost, the lack of interpretability. With millions of free parameters, it's unclear what mechanisms they are using to make decisions, and adversarial examples, tiny perturbations imperceptible to humans, in the input can lead to significant changes in the predictions, which hints that these mechanisms work very different from what we humans do. And interpretability is necessary for many use cases. Some of them are, for example, high reliability. Interpretability is not always needed, but it's important for some prediction systems that require very high reliability, because errors in those systems can cause catastrophic results, such as human lives, for example, for airplanes, heavy financial loss, and many other cases. And interpretability can make potential failures easier to detect with help of domain knowledge and avoiding severe consequences. There's also ethical and legal requirements. One, for example, is to avoid algorithm discrimination. And there's also legal requirements for interpretability, such as in Europe, that require a right to explanation, where people have the right to be explained why an automated decision made their decision. There's also scientific uses, such as then when deep learning models are applied to sciences and they discover new insights about the world or whatever science they're studying. It's important to understand what exactly the model came up with, or what knowledge does the model have, so that we can learn from the scientific discoveries made by models. And finally, and probably the most important to you all, is model debugging. Interpretability can help us understand if our models are looking at data features in the way that we expect them to, or if they're picking up on spurious features that are undesirable. And here's an example for natural language. This is a masked language modeling task, very common in today's days. And The models are asked to predict what's the most likely word in the mask. And we can see that like by changing the gender pronoun and by looking at explanations, we see that like the model is heavily relying on the gender pronouns. And this is a bias that might not and should not be desirable for most use cases. And if this was our model in production, if we had access to the explanations as we see here, we could take steps to address this bias by, for example, collecting more data or introducing debiasing approaches for our model so that it doesn't rely on these spurious bias features. So yeah, but what is interpretability? Well, this is a very controversial, I wouldn't say controversial, but very rough area where it's not very clear how we define interpretability. I'll point out one definition from this survey on network interpretability, which says that interpretability is the ability to provide explanations in understandable terms to a human. What are explanations? There can be natural language utterances, logic rules, or something else. And by understandable terms, we mean terms from the domain knowledge, such that a domain expert can evaluate these explanations. Here are some examples of interpretable terms used in practice. For computer vision, normally if you consider images, patches of images or superpixels can be considered as interpretable terms. And visual concepts such as objects and sets of objects can also be considered as interpretable terms. For natural language, if you consider a sentence, words or subsequences of the sentence can be considered as interpretable terms. And for bioinformatics, motives are interpretable terms of the sequences. Also, common attributes that people consider when talking about explanations or interpretability are that explanations should be readable, as in we humans should be able to interpret the explanations. They should be plausible, as in explanations convinces humans about the way the model is working. And they should be faithful, as in they represent the underlying model decision process. And note that none of the factors here described implies the other. For example, the model weights are very faithful explanations of the model because they represent completely the underlying decision process. However, they're not readable at all. We cannot look at the model weights and understand as humans what the model is doing. And similarly, explanations can be plausible but not faithful, and faithful without being plausible. And this can be very dangerous because if an explanation is plausible, as in it convinces us humans that this is how the model is working, but it's not faithful, and so it doesn't represent exactly how the model is working, it can lead to very serious consequences, such as leading us to believe that, for example, a model is not being biased, well, and in fact, it is relying on biased features. And yeah, so this is a general definition of what is interpretability. So let's look at some interpretability methods. I'll go over some of them and try to explain them, but not in too much detail. Feel free to ask me for references, and references will be included in the slides. A very well-known one is LIME, or Local Interpretable Model Agnostic Explanations. And this model works by perturbing the input to seeing how these perturbations affect the predictions of the model. For example, we can remove certain pixels around the original image and see how this changes the prediction. With this new data set collected, we train a local approximation of the classifier using a simple explainable model, such as a linear regression. And based on this, we're able to create these patches that seem to represent particular output decisions. We can see, for example, here that the guitar seems to be highlighted. Part of the string seems to be highlighted for electric guitar. Part of the body of the guitar seems to be highlighted for acoustic guitar, and the actual dog is highlighted for Labrador. Another example are LRP, integrating gradients, and various other methods related to this. These methods work by extending the backpropagation rule, by introducing a custom computation on the backward pass. Each of these methods introduces its own variation, but overall they tend to backpropagate certain relevance and produce a saliency map or like parts of the input that represent the prediction of the model. Another example are attention-based explanations. Attention-based explanations work by leveraging the fact that the recent models, such as transformers, rely heavily on the attention mechanism, which produces coefficients relating every part of the input to other parts of the input. For example, here we see in machine translation, the attention of, for example, an RNN says how relevant U is todavia and how relevant at is to casa. And we can take this attention maps for a particular word, for example, for the end token that we assume is representative, and assume that this conveys an explanation for the input. However, there are some controversies on the field regarding how faithful these explanations are. See, for example, I didn't include here the link, but see, for example, attention is not explanation, and the attention is not no explanations. That makes some arguments why should we and why should we not consider attention as explanations. There's also a line of work on contrastive explanations that attempts to consider recent studies on social sciences that establish that we humans explain our decisions in a contrastive fashion, so comparing an outcome compared to other outcomes. And we can assume that the previous methods do this implicitly by comparing why is this outcome rather than all the other outcomes. And we see, for example, here that when we say why is dentist, we implicitly are contrasting against why is this dentist and not any other thing. And in this work, they propose explicit contrastive explanations by considering why is an outcome rather than another explicit outcome. And they do this by doing some fancy projections of the network representations to latent space that only considers features relevant for the two outcomes in consideration. So yeah, this is another line of work that is similar to the other ones, but it's contrastive. And finally, very different line of work. So the previous explanation methods were mostly local, example-based explanations that aimed at explaining how the constituents of the input are important to a decision. And this method here shows another kind of explanation, which are called global explanations, that tend to try to show how the network behaves generally, irregardless of the input. So in this particular method, they come up with why certain neurons, when and why certain neurons trigger. And for example, we see that certain neurons in a network trigger, particularly when the input has water or is a river and is not blue. And they represent the network as a composition of these explanations. So yeah, this is a different line of research that tries to bring global explanations rather than local explanations. And so yeah, we have all these explanation methods that try to provide different perspectives on the inner workings of a neural network. And if you ignore the last example, explainability example, these methods tend to produce different explanations of the output prediction given an input. And the curious thing is that these explanations might not always match. For example, we see here that we have three different explanation methods: line, input gradients, and attention. And this is for an example that is classified as negative. It's a movie review that's classified as negative. And we see that the different explanation methods highlight different words. For example, the first one highlights bad and natural, poor. The second one seems to be highlighting this for some reason, especially was, not very plausible to us. And the third method highlights also bad, dialogue, unnatural, poor. So yeah, we see that these methods seem to highlight different parts of the input. And it's unclear a priori which one of these methods is better. We can analyze and compare them to what we humans would consider as the most important, but this would be purely measuring plausibility and not faithfulness. So we would only be trying to see how much the model convinces us that these explanations are, in fact, what the model is doing, but they don't actually measure what the model is doing. And also there's other lines of research that try to compare explanations to gold standard human annotations, but this also doesn't measure directly faithfulness. It mostly measures plausibility, and even measuring plausibility is quite limited because there could be other plausible explanations that get low score when compared to the gold standard annotations. So yeah, what the community is lacking is a standard quantitative measure of faithfulness of explanations. So a measure that tells us, okay, this explanation seems to be hinting how the model is actually performing its computation. So yeah, now I'll present two different approaches for this particular problem of evaluation of faithfulness of explanations. The first one is a communication game by Mark Servizio and André Martins. In this work, they framed the explainability problem as a communication problem. As this figure shows, basically they have a classifier. They give the classifier the input and the output of the classifier plus some inner workings of the classifier to an explainer module. This explainer module produces an explanation or message that's fed to a layperson. And so this layperson, given the message, needs to try to predict the model's output. So we're not measuring directly the correct label, but we're trying to get the layperson to correctly predict the classifier's output. This is called simultaneity, and it's a way to see if the explanations are faithful. Why? Because given that we don't pass the input to the layperson, we just pass the message should convey most of the information needed by the classifier to predict a given output. And in this case, good explanations are the ones that communicate well the information to the layperson. And in this work, they compare a bunch of different explainability measures to each other. This is on natural language processing. And based on this, they come up with some conclusions, such as that sparse attention-based mechanisms seem to have a good communication success rate and seem to be better than gradient-based methods. And yeah, this provides a framework for evaluating the faithfulness of our explanations. So this framework has, despite this, some downsides, in my opinion. The explainer has access to the label. Why is this a problem? Because this can lead to a thing called the trivial communication protocol, where basically the models learn to pass the label directly to the input. And so the explanations, while faithful, do not provide, they're not faithful to original input, but while they do provide all the information needed to predict the output, they're not plausible to us humans, and they're not faithful because they don't provide insights on how the model is doing the computation. Also, the layperson only has access to the message, not the inputs. And this is not necessarily bad per se, but it ties with the third point that says that the explainer is needed at test time. So when we're measuring the performance of an explanation method, we need to have the explainer. And this is not necessarily bad, but in my opinion, it makes the framework, how do I say this? Not as general, because ideally we would like to evaluate how the explanations help the student predicting without the explanations at the end of training. And so now we'll see another framework for evaluating explanations that tries to address some of these issues. It's how much do explanations from teachers aid students, by Dennis Prudy. And in this framework, they propose evaluating explanations to the degree in which they help a student model in learning to simulate teachers on future examples. What do we mean by this? And we'll see here in this diagram. In a normal setting, we have a teacher, and the teacher has the input and its output. And if you train a student to try to predict the teacher's label, this is the standard setting, and this is a baseline. Now, let's assume that we give to the student also, plus the input and the output, also some explanations. So at training time, our student has access to these triples, and at test time, we just give the input. The idea is that if explanations are good and faithful, our model trained with the explanations will be able to achieve a better simulatability, as in the ability to simulate the teacher, and it will achieve a better simulatability than a student trained without any explanations. And this is the overall idea. If an explanation is good, it will help students learn to simulate the teacher in less examples, or simulate better than a student that is not given explanations. So yeah, comparing to the previous framework, this doesn't require that explanations are used at test time, and so it's different. It is not necessarily better, but I tend to agree that this is a better framework for evaluating explanations. And we see here that in their work, they compare a bunch of different explainability measures, explainability methods, such as LIME, the gradient-based approaches, and attention. And in their work, they seem to see that like attention-based explanations seem to help students to learn to simulate the teacher better than the other explainability approaches. To note, however, that there could be some biases in this study, in the sense that both the teacher and the student models are transformers. So they rely heavily on attention mechanisms. So it could be due to this that attention-based explanations are better than the other explainability methods. And it would be interesting to see if this comparison also works for example, the case where the teacher is in a transformer, but the student is an LSTM, or both of them are LSTMs, and if these conclusions about which method is better would still hold. But nevertheless, this paper introduced a general framework for evaluating explainability with regards to faithfulness. Both this and the other framework. And so yeah, both these frameworks introduce this notion of evaluating faithfulness by how well do students learn from a teacher. But in none of these frameworks does a teacher necessarily have to be a model, a machine learning model. When we think of explainability, we mostly care about how explainability with regards to humans. So how readable the explanation is. And so there has been also some work that tries to mimic this teacher-student evaluation framework with respect to human students. So in this example here, we see that this is basically a data set of genuine reviews and fake reviews, and the model is trained to predict either if this is genuine review or a deceptive or a fake review. And in this framework, they basically have a model trained on this, and then ask a bunch of humans to try to predict the correct label. So if the explanation is genuine or deceptive, and they basically compare how a human would do without any explanation, so the control setting, given examples, and also giving some explanation methods, just highlights, heat maps, and curiously, even the predicted label of the model. And we see here that, like, even for humans, explanation methods are in fact useful because they help the humans perform better on the task at hand. So in this case, in the teacher-student framework, the models help, the explanations help highly the humans to predict the correct label. And interestingly, even when given the label produced by the model, humans still achieve less than the model's prediction, less than the model's performance, which seems to hint that humans don't trust either the model's prediction or the plausibility of the explanation. So this is just an interesting, let's say, insight of this paper that I found curious. Okay, so this is all a discussion about previous work that was done to evaluate explanations and some methods to produce explanations. Let's try to see some work that we've been doing at our lab, which is, can we use this to learn better explanations? So the previous work has provided explicit metrics to evaluate explanations. And overall, these methods can be summarized as good explanations make the students learn faster and more sample efficiently than a student that is not given an explanation. So the question here is, can we use this feedback to train our explainability methods? So can we try to use this as an explicit learning signal to learn better explanations? And this is a very convoluted method because when training the student, we have an optimization procedure. So we need to overall pass this training signal towards the teacher. So this is a very complicated procedure, but fortunately, in the last few years, there's been a concept known as meta-learning that addresses exactly this problem. And so currently, we're trying to see if not only can we evaluate explanations quantitatively, but if we can use these quantitative methods to improve explanations. And research questions that we're currently asking ourselves is, first of all, obviously, if this will lead to better explanations in terms of faithfulness or simultaneity, if explanations will be useful to humans overall or readable. So it's not clear if after training the explainability method, even if in the beginning it was readable to humans, if it will still be readable to humans at the end of the training procedure. And finally, how well do this explainability method generalize across either architectures, seeds, training runs? But yeah, overall, this is some research we're doing. This is very work in progress, but I'm happy to discuss in the QA afterwards if someone wants more detail. And I guess I wrap this quite quickly because I'm getting to the end. But to conclude, interpretability is a very useful and important concept in machine learning. It can be useful for model debugging, ethical reasons, and all the other reasons I pointed out at the beginning. There are many approaches to bring interpretability to our models based on different principles. And we're just now scratching the surface of how we can compare these methods with each other. But hopefully, future research will try to address this more. And this has been a very recent concern. So I'm quite optimistic that in the next few years, you'll see better methods to evaluate explanations with respect to both humans and machines, readability, faithfulness, plausibility, and that we'll see better explainability methods overall. And yeah, that's it. I guess I was quite fast.
Okay, Patrick, you did wrap this up pretty quickly.
People are busy, so.
Okay, so I think I'll just start by asking you a bit more about the details of the project that you were briefly mentioning about meta-learning.
Yeah, sure. Let me try to go back.
So I didn't want to. Let me put this both. Okay.
So I didn't include too much details because it's still not super set on stone exactly what we're doing. But the idea here is that I can try to go a bit in more detail since we have time. Basically, the idea is that so when we optimize the student in the inner loop, all the operations in the inner loop are differentiable. So the optimization procedure itself is differentiable. And so by training, let's say, a student for n steps, we can measure the performance of the student at the end of the n steps on a validation set and checking how well does the student do given the explanations at the end of n steps. We can then backpropagate through the inner optimization loop, and this leads to some nasty stuff like Hessians and second-order derivatives. The point is, we can do this, and we can use this to optimize our meta-parameters. And meta-parameters are the teacher explainer parameters. So if you run this loop, inner loop, outer loop, multiple times consecutively, we should be able to, at the end of many iterations, reach or optimize our teacher such that its explanations are better at teaching students. I don't know if this makes sense. Maybe I'm being a bit confusing.
Okay, so just to follow up on that, so you're always assuming that the explanations will be generated automatically with no sort of human imputation?
Exactly. So actually, this has an even stronger requirement, which is the explainability method needs to be differentiable. So because we need to backpropagate gradients, we cannot use certain methods. I'll go back a bit. For example, we see here in Travis's work, they have this top K operation, which extracts the top K tokens of the attention. This top K operation is not differentiable. So if we were to use these explainability methods in our framework to train better teachers, we cannot do it because there would be no gradient. So yeah, it requires automatic explanations, not human explanations, but not only automatic, but differentiable explanations. I don't know if this answers your question.
What would be an automatic explanation in this case?
So for example, let's think attention. You have a BERT model. A common way to use attention is to use attention. So if you just extract the mean of the last heads, that's an automatic explanation method.
Yes, and it's differentiable because
attention computation is differentiable. Yeah, exactly.
Okay.
Another one is, for example, Lime is not differentiable. It's automatic as well, but it's not differentiable. And yeah, so there's this different explainability methods. In this work, you're just addressing a class of explainability methods and try to see if you can make them better. But yeah, very early work in progress. I don't want to give too much details that will not be included.
Okay, so just to see if you think it would be an interesting approach. I've read some work recently that also a common strategy that they use whenever they want to have something that is differentiable and they don't have it is like to perform some relaxation using some kind of function like the sigmoid or so. So maybe that might also prove useful in future research. I don't know.
It could review. The problem is that like some methods by themselves very hardly can be made interpretable. Let's take, for example, Lime. Lime works by perturbing the input and building a linear classifier. Both these perturbations and the classifier on itself are non-differentiable. So it's not very easy to get. So the operations needed to build a Lime explanation out of an input, most of them are not differentiable. And there's no easy way to get differentiability in it. So I think that not all methods will be able to be encompassed in this framework. But I do believe that, like, yeah, I agree. There are some methods like score function estimators or reinforce that could be useful to get gradients of non-differentiable methods. But we're still not going there because they bring all other sorts of problems like variance on the gradients. And so we're going to start simple, softmax-based explanations and attention-based explanations. And gradients, because gradients themselves are differentiable. For example, we see here, let me show Danish previous work at all. So for example, as I said, Lime is not differentiable, but gradient norm, gradient integrated gradients are differentiable. You just take the gradient of the gradient, and that's a gradient of an explanation, basically. So yeah, you did bring some points, but even for Lime, I don't believe Lime you could put reinforce, but for other explainability methods, non-differentiable explainability methods, you could eventually have some sigmoids or score functions that would make them useful for our framework.
Okay, thank you so much, Patrick. So we'll take a look now at the questions at the chat. So I'm going to start with this one. So what is your opinion on white model explanations versus model agnostic explanations? So it would be the ones that look at the model versus the ones that do not.
So I have a biased opinion. Maybe this is not opinion shared by everyone. I strongly believe that in the future, explainability methods will be in model, as in, I believe that explainability methods that look at model will be much stronger than model agnostic explanations. Why? Because by not considering the model inner workings, you're severely limiting yourself in the information you can use to make predictions. For example, Lime. Lime works by perturbing the inputs and doing this linear classification. and yes, it produces explanations that seem reasonable and plausible, maybe even faithful. But the guarantees of faithfulness are very weak because, again, they don't look at the model itself. So how can we be sure that they're faithful? So I strongly believe that future work will eventually prove me correct that model-based or explanations that look at inside the model will be better suited, more faithful, and plausible than model-agnostic explanations. I don't know if that answers the question about my opinion.
I guess so. And also, as a follow-up on this, do you think that either one of the categories is more prone to being like a target of those adversarial attacks or something like that? So there's been some work on that as well in the literature.
Yeah, so regarding adversarial attacks, so one problem with, so the trade-off with this access to the model inner workings is that, particularly because they have access to the inner workings of the model, I think that explainability methods with access to the inner workings of the model will be more prone to adversarial attacks. Because by the fact that they have access to the inner components of the model, a potential malicious user of this model could look at the explanation, see, okay, the model seems to be doing this, and we can try to maybe look at the gradient and try to change the input such as it produces this different output. So with respect to attackability, as we want to call it, or adversarial attackability, I believe that model-specific or in-model explanations are more suitable for this kind of attacks. But I don't have too much knowledge on this particular view of things.
Okay, thank you. So going on to another question from the chat, I'm going to take this from you, Pinheiro, which is asking what is the most used explainability method?
It highly depends on what we call industry. So I have some experience in industry in big tech, and highly depends on the model as well. For example, for medical industries, because explainability is such an a priori concern, what happens is that because of this faithful problem where we don't know exactly if these explanations tell us how the inner workings of the model, if the inner workings of the model's decision process, when the explanations are crucial currently, people in the industry tend to go for natural interpretable models, such as decision trees and SVMs, because these come for free with interpretability. But for example, for when we cannot do that and we require a deep learning model, and so that explanations are not faithful by nature, what I see in use is that the first approach is to look at attention coefficients. Why? First of all, it's very simple to do. It comes with your model, and you just look at some heads, you average them, and you look at them. So I would say that probably attention would be the most used method in the industry. But again, my experience is quite limited, sample size 1. But if I had to bet, I would say definitely attention because of the ease of useness, and because they seem to be decently good explanations, despite all the controversy regarding attention is not explanation and attention is not explanation.
Okay. Okay, so taking a look at other questions, we have here João Gant asking us what your thoughts on chat, because I think you haven't mentioned, or these works haven't mentioned it, and in algorithmic
Shapley values.
Yes.
I'm not too familiar with them, honestly. I kind of glossed over the Shap paper, so I'm going to be honest. I don't know exactly my opinion. I don't have a strong opinion about Shapley values because I didn't, research too much about them. So I'll prefer not to answer that because I might say something wrong and mislead the viewers.
Okay, cool. So this one seems rather interesting as well. So do you have any thoughts on how causal can be used for expandability?
Yeah. So the whole point of expandability is to discover the underlying causal factors that leads to a decision. So I strongly believe that causal inference could be useful for explainability methods. In fact, if there was an easy way to use causal methods in our current deep learning frameworks, they would almost definitely answer the explainability problem. However, there's no clear way to use causal inference in deep learning models. So this is almost a mixed answer, which is yes, they could be very useful for explainability methods. However, there's no clear way to incorporate this causal inference and causal discovery methods in deep learning networks. So yes, overall, I do believe they'll be very useful. In fact, I do believe they would solve the problem of explainability.
And what do you think it's missing in order to be able to use this technique in deep learning? So is it a question also of the dimensionality of the inputs? For instance, in NLP, for instance, we have a large vocabulary, and how do you see? Do you have any thoughts on that? On how this could be applied to NLP?
So my how do I say it? My very limited knowledge of causal inference is that like it normally sometimes requires a priori that you specify the causal graph. So how the particular parts of the input relate to each other and how they influence each other. While the current paradigm of deep learning is just get the data and let it discover correlative relationships by itself. So there seems to be a mismatch between specifying a priori the causal graph and letting it discover the relationships. The most promising approach I would see is the area of, I'm not very familiar, but of causal discovery, which tries to automatically infer the causal graph. And I think if we were to go about incorporating these methods for deep learning models and eventually to extract explainability, I would probably go about that route. But again, I'm not very familiar with causal inference literature and how it's applied to deep learning. So I don't want to say something too wrong on this.
Thank you, Patrick. So let's pick another one. Okay. Okay, so let's pick this one from Inish. Inish is on fire here with these questions. Okay. How can we be sure that the explanations are in fact true when we are using an explainability model that is actually also a machine learning model?
Okay, so there are a couple of things we need to disentangle here. So what do you mean the explanation is true? So the truthness of an explanation is a hard concept. Do we mean faithful?
So I guess it would be something like that. I don't know if Inish is still around, but I'd say that, like, because I think that the way this question is going is like explanations are meant for human, and we are basically doing all this process in teaching a student and learning from the teacher and whatnot, and we are only using things that are generated automatically. And how can we be sure that these explanations will be suited or will like address the information needs from the humans? Or how do you see the humans consuming these explanations? Because you might be biasing the explanations to something that they shouldn't be. I don't know. This area is a bit fuzzy, right?
So one particular problem with like interpretability and explainability is that like most stuff is not very well defined. It's not clear what concepts we mean. So I'll disregard the truthness of an explanation here because it's not clear to me what's truthness. I'll mostly say regarding to the concepts that I said in the beginning, which is history. And so I'll tackle readability and faithfulness. And so readability normally tends to be by design. So when you come up with an explanation method, we almost always make sure that like whatever comes out of our explanation method is interpretable by humans. So let's say for example, attention maps are very easily readable for humans because they just highlight words. All right. So I would say the first answer is by design. Regarding faithfulness, and it's a bit much harder. And this is the whole point that I was trying to make, is that it's very hard to evaluate faithfulness, which I assume is what you mean by explanations are in fact true. Because you're right, it's not because they're machine learning models. They could be saying, they could be plausible, as in they convince us humans that this is what they're doing, but in fact they're plausible but not faithful, as in they don't actually represent the underlying decision process of the machine. So in order to be sure of this, I strongly believe, based on what I presented, that evaluating explanations with regard to either this framework or this framework could hint that, because if a model is able to simulate another model with much less examples based on explanations, my intuition is that these explanations need to be telling us something about the underlying decision process of the teacher. Otherwise, it would be really hard for the student model to learn as sample efficiently as it is learning. So my point is, to summarize, I cannot make guarantees about the faithfulness, but I strongly believe that, like, to try to make some assertions about it, we should be using one of these frameworks to evaluate our explanations.
Okay. So let's pick. Thank you, Patrick, by the way. So let's pick another question. What do you have to say about counterfactual predictions as a proxy for explainability?
By counterfactual predictions, you mean something in the? I assume you mean something in this framework here of contrastive explanations. If so, I think this is a very interesting work. I do believe that the sum of the points they make about we should consider explanations in an explicit contrastive setting is important, because it can make explanations more focused about what we and users particularly want. I'll say this particular example, it very strongly illustrates the point, because when you try to point out why this is a dentist, the explanation highlights a lot of stuff, and we as users might not be interested in seeing all of this. So by having a contrastive decision, or contrasting our true outcome to another outcome, we're able to get more fine-grained explanations that helps us to interpret the underlying decision process of the model with regard to one decision versus another. So if I recall correctly, the question was okay. So you mean I saw there was another point regarding counterfactual is in modifying the input to get opposite predictions. Yeah, I think this goes in the line of research of the Lime model, which is what Lime does, which is you try to modify the input to get an opposite prediction. I think it's a promising way, but again, as I said, this tend to be very, at least most of the models I've seen tend to be very model agnostic ways. And so while they have a benefit by being model agnostic, I think there can be wasting a lot of important information about the model inner workings, because they just work based on the input space. However, I definitely think it could be interesting to have some sort of middle approach where we have some knowledge about the inner workings of the model in our explainable method, and we couple this with some Lime-style counterfactual explainability method. And I think this could be an interesting factor. But just purely counterfactual explanations, as you mentioned, modifying the input to get different prediction, I see them as not as promising as model-based explanations.
Okay, thank you, Patrick. I think that was enlightening. So let's pick another one. This one is a bit more outside the realm of NLP. So how do you see explainability apply to different tasks outside NLP?
I mean, it's been done. As I said, medical data requires explainability as a fact, because of the whole legal procedures a lot around making automatic decisions for patients. So explainability is definitely being researched and applied to medical data. In fact, a lot of these methods that I presented were not originally proposed in the natural language field, but were proposed in computer vision, for example, where it's also very easy to propose readable methods. So I think a lot of these methods that I mentioned here are very easily applicable to computer vision. But not only that, I think for example, the model agnostic ones, by nature, they're model agnostic, so they can be easily applied for any machine learning model in general. Integrated gradients, as long as the model is differentiable, we should be able to get input saliency maps, so it could be applied to computer vision, NLP, or any other, literally any other task. And attention-based explanations, given the recent surge in transformer-based computer vision models, they can definitely be applied to computer vision as well. And transformers have recently been applied for medical data, not biomedical, we call it genome data, games. So I think most of these methods can very easily generalize to other domains outside NLP. So to answer your question, I think most of these methods are not exclusive for NLP, but can be very easily generalized to other domains as well.
Okay, thank you, Patrick. So there's another question from Luis in the chat. Do you know deep learning debug tools that are based on these models? Or... Yes.
So if I'm not mistaken, let me try to find it. Hugging Face had an attention visualizer, which a lot of people seem to be using. It was a Ortiz, was this one? It was an ACL paper, I think. Let me check. It was quite a cool thing, but you could just take any model with attention layers and you could look at it. Let me try to find it. But this requires obviously that your model is based on the attention mechanism. Overall, debug tools, very explicit debug tools that you can just run in your, how do I say it, in your normal day-to-day deep learning framework. I don't know of any. But yeah, for particular models like transformer models, there are some. I'll try to find them and link them afterwards, maybe in the GitHub repo or something like that. But yeah, there are some. I wouldn't call them debug tools because they were not made with that purpose, but people have been using them as debug tools for their transformer models, attention-based models, and stuff like that. Regardless, you can just take any interpretability method and it should work as naturally a DL debug tool. There just isn't anyone available that I know of yet. But yeah, I'll try to link the visualization, attention visualization tool.
Yeah, we'll make it available afterwards. Just as a follow-up on that, Patrick.
Okay, I found it. I can try to share it. How do I share it?
I'm sorry, there's been a technical problem. So follow up on this, because you just went dark, so I was thinking that it was a problem here on the platform. Okay, so just as a follow-up, do you think that a single method would suit the needs when debugging a model? Or let me rephrase this, I'm sorry. So in this case, I'd say that in-model explanations would be much better suited for model debugging than just the ones based on perturbation, right? So what are your thoughts on that?
Again, because it's not clear yet what exactly, how these different methods compare to each other in terms of faithfulness. I strongly believe that single method is not gonna, it might work, but you're not gonna see the whole picture. So if someone were to develop a DL debug tool, I think a very strong requirement would be different methods to try to capture the different properties of the model. And so, no, I don't believe a single method would work. However, I do believe that a strong point in any method that would be included would be easily the readability of it. Because even if the method is really faithful, such as the weights, if we as humans cannot do anything with them, it will not. We cannot do anything to debug our model. So my point is we should use more than one interpretability method, and all of them should be highly readable so that we can take information from them in debugging our model. So yeah, not a single one, multiple dems, preferably all of them quite readable.
Okay, thank you, Patrick. Okay, just so I'll pick this one as the last question, and then we'll wrap up this session. So this is quite large question. Explainability is advanced in fields where the models are better than humans, for instance, NLP and computer vision. How can we assess an explainability when the model is far better than a human, for example, in tabular data?
Again, it's quite hard. Like, it's a very difficult problem. And here, what we mean by assess is, again, almost the chicken and the egg, because it's hard to assess. The definition of assess is very underdefined in the explainability area. I would say, in terms of plausibility, the only way is to look at it and say, okay, this seems to be what we as humans would do. That's one way to do it, is qualitative analysis. For faithfulness, especially in these cases where the models are much better than us, I strongly believe, as I said previously, that we need one of these new frameworks for evaluating based on a student to be able to tell if the explanations are good. Because that's the only way, if the models are that much better than us, that's the only way to make sure they're good explanations, is to get another model to try to learn with those explanations. Be it another model or we humans, because as I said, this teacher-student framework doesn't require an actual machine student. It could be a human student. So I'd say to evaluate these models that are much better than us, we get them to output explanation and see if we can simulate to the degree that it's possible the model's decisions. And that's how we should evaluate with regard to faithfulness the explanations of these models that are much better than humans.
Okay, Patrick, thank you for all your time. I think I'll wrap up this session. So for everyone watching, this video will be available offline on YouTube, and the slides will be published on our GitHub repository, as well as the links that Patrick mentioned throughout the presentation. So I'd kindly ask you all to fill in the feedback form that is available in the meetup. And yeah, every link will be in the description. I'll also ask Patrick to fill out the form after wrapping up this session. And I'd like to thank everyone for participating in this discussion. Thank you so much.
Thank you.